our next talk. We'll be talking about sketching for proving generalization of support vectors.
Right. So yeah, thanks a lot to the organizers for inviting me. So I guess in this one, maybe in contrast to the other, I guess, learning, machine learning related applications of sketching, this one is actually not using sketching for designing new algorithms, but instead actually just for purely theoretical analysis of support vector machines. So I'll try to get back to it. And I think the talk is going to start out slow, just motivate support vector machines, and for those not familiar. And then in the latter half, I guess it'll be more technical. So I guess, speaking of support vector machines, here we're talking about classification problems, to keep it simple as binary classification. And so maybe imagine that you have a smartwatch and you want to predict whether the wearer of the smartwatch is on a bike or in a car. And maybe you have some measurements like the speed the person is moving at and maybe the heart rate, and you have to figure out whether you're driving or biking. So maybe the data could look something like this, right? The blue dots are people on their bikes, some training data that you collected, and the triangles, the red triangles are people that are in their car, and maybe there's this thing, you know, if your heart rate is high and your speed is low, maybe you're on a bike, or vice versa, right? If you're going very fast and you have a low heart rate, maybe you're in a car, or maybe, you know, this is maybe an idealized setting. I guess you could have a very nervous driver with a high heart rate. But anyhow, I guess this roughly looks, this is what you would expect, right? Low heart rate, high speed tend to be people in cars and vice versa. So the idea here is, given this training data, I guess we want to train a classifier so that given a new data point, without its label, we can make a prediction as to what the label is, right? So is this square out here, is this a car or a bike, right? And I guess just staring at the picture, I guess we would probably guess that this is someone on a bike, but maybe we can do it a bit more formally. So for linear classifiers, we're going to train a linear model, right? So just a hyperplane, and everything on one side we're going to classify red, and everything on the other side we're going to classify blue. So maybe this line here could be a good model to train, by looking at the training data, right? It definitely perfectly separates the red class from the blue class. And so maybe we can use it to say everything below the hyperplane is someone on the bike, and everything above is someone in their car. Maybe a little bit more formally, I guess when we're doing this linear classifiers, I guess we'll describe our input elements as feature vectors, just a vector of d numbers. And the labels will be -1 and 1 in this case. That's the most standard setup. And then the parameters describing this linear model is, I guess there's a normal vector having coefficients w1 to wd, and then a bias b. And the way, once you have such a set of parameters, the way you make predictions on a new point is just you compute, I guess, the inner product between your normal vector and your feature vector x, and you add the bias, and you take the sign of this. So I guess it looks something like this. This w is describing the normal vector of the hyperplane, and the bias is basically describing the offset from the origin of this hyperplane. And so, of course, the question is, once I have such a data set, how do I find this nice hyperplane in this picture? And there's several different algorithms for doing it. I guess the simplest one is this perceptron learning algorithm. It's a classic one. So this perceptron learning algorithm is, given this data set, how can I find the bias and this normal vector of a good hyperplane? And here, I guess we mean that the hyperplane or model is good if it classifies most of the training data correctly, or all of the training data correctly. And then I guess the general idea is that if we have good performance on the training data, hopefully we have good performance on new data as well, right? When we need to make new predictions. I'll come back to this in the last half of the talk, doing it a little bit more formally. So this perceptron learning algorithm, I guess, is the simplest algorithm you could almost come up with. So the algorithm is, I guess you initialize the parameters to, let's say, 0 or randomly, and you do, while there's a data point in your training data set whose label is currently being mispredicted by the hyperplane, right? So you look at what prediction would I make, and if this is different from the actual label, I found a wrongly classified point, and then I update my model by saying the new w becomes w plus y times x, and the bias is b plus y. Right? So the intuition for this step is that you're going to make your model more correct on this misclassified data point in some sense, right? So maybe, and then when you're done, when there are no more points that are misclassified, you return this model that you found, right? So in a picture, I guess if you're in some iteration, maybe your bias is currently 0, you have this vector w here, you look for a point that's misclassified. In this case, this point up here is misclassified. So what you do is, I guess you change your W by, you take the vector x here, you multiply it with the label. In this case, the label is -1. So you subtract off this vector x from your W, get a new W. And I guess you also change the bias by, I guess, adding the label of -1 to the bias. And so I guess the new model you have is this one here, right? So you kind of, you change your hyperplane a little bit and you shift it based on this misclassified point. Of course, as you can see right now, it's correct on this point, but it became wrong on another point. So actually you can introduce new mistakes by running this algorithm. And it's not even clear that it gets better with every iteration when you're running this perceptron. And so it can become wrong on new points. So I guess you can ask, isn't even a good algorithm will even find a good hyperplane? And this is not obvious, but you can prove that if the data is linearly separable, right, meaning that it is a hyperplane that perfectly separates the data, then eventually, if you run it long enough, you're gonna find a separating hyperplane for this data. And this is not trivial to prove. So linearly separable, I guess, just mean that it's possible to draw this hyperplane that nicely separates the two classes. So this is linearly separable. Okay. Now, of course, if I have some training data that looks like this, and you run this perceptron learning algorithm, you just get some separating hyperplane, at least in the vanilla version of perceptron. So of course you can ask yourself, right, are all hyperplanes equally good at making new predictions, right? So in this case, this is a separating hyperplane, and if you use this one to make new predictions, I guess this point will be predicted as blue because it's below the hyperplane, and that one down there will be predicted as red. And this is, at least when we stare at it, this might not be the right way to make these predictions. And probably this hyperplane here, this looks better at making predictions. Just at least staring at it. So of course you can ask yourself, what is it that makes us prefer the second hyperplane to the first one? And I guess the intuition is that this second hyperplane there's a large gap or margin around it where there are no data points in it, right? So there's really a big gap here out to the nearest training points. Okay, so this is, I guess, a large margin separating hyperplane. And I guess this is the intuition behind support vector machines. In support vector machines, you train a model that is basically the largest margin separating hyperplane. That's the one you aim at finding, at least in the simplest version of support vector machines. And that's the only one we'll look at here. So in this talk, I guess we'll assume that it's linearly separable, and we'll always just look for the largest margin separating hyperplane to the nearest point. So I guess we need to define what are these margins formally. And I guess if you just have your W and your B, then you can look at this prediction that you're going to make before taking a sign. If you compute the inner product between W and X plus a B, it's really a sign distance to the hyperplane that you get out, right? It's basically how far is X from the hyperplane up to a scaling of W and B. I can always represent the same hyperplane by scaling W and B up and down by the same factor. So because of this scaling, we're going to assume that this normal vector has unit norm, right, from here on. So W always has unit norm. Then the margin on a training point, xi, yi, is just, you look at whatever you would predict, the sign distance from the hyperplane, you multiply it with the label yi, and this value is what we call your margin. Okay, so I guess it's still a sign distance, but multiplied with the label. And so you can notice that, I guess if this is a positive margin, it means that your point is basically classified correctly, right? If I return the sign of this, it must be the same as the label, right? If this is a positive number. And likewise, if it's negative, it means that you'll wrongly classify the point. And the larger the number is, the further away from the hyperplane the data point is. So I guess in this case, right, everything on this side has a positive number before you multiply it with the label, and everything up there has a negative number before you multiply it with the label. And so I guess the red points will have a positive margin, and so will the blue ones. And that is basically the simplest version of support vector machines, is just solving this optimization problem, maximize over the choice of WB and margin gamma. I guess you have a constraint that says all the margins should be at least gamma. And let's say you insist on the norm of W being 1. This is not a convex formulation. I guess the last constraint there is not so nice, but there are ways of solving it, right? And I'll not get into that. That's not the point of this talk. So, but that's basically what support vector machines are finding, right? They're finding the largest margin separating hyperplane in the simplest version. And I guess they're super popular in practice. I guess you probably all know, right? I think the original paper has more than 50,000 citations. It doesn't happen for a theory paper. And I guess the thing we're trying to do here in this work is, can we try to give some theoretical justification for why it helps to have large margins in this model, this linear model that you're finding, right? So can we prove that there's some benefits to having large margins? I just want to say we're not the first one. I guess we'll come back to who the co-authors are. We're not the first one to do this. This has been done a long time ago. I think maybe Peter Bartlett was one of the first to initiate this kind of study. But we improved on some of their bounds. So to study theoretically, I guess we'll have to make some assumptions on, if you want to prove that this has a good performance, we need to assume something about how the data is obtained and what does new data look like. And I guess the standard way to look at it is in this packed learning framework, where I guess the training data is assumed to be NIID samples from some unknown data distribution. We don't assume anything about the data distribution, but only that we get these IID samples from it. I guess technically to prove something, we will assume that the norms of all the data points are bounded by 1. I guess you could always scale things up, but that will affect the bounds. And it's supposed to, because I guess the margin here, if I scale all the points by a factor 1,000, the margin of the same hyperplane also scales by a factor 1,000. So it should depend on somehow on the magnitude of the norms of these vectors. And the assumption is that, that the new data is going to be similar to the training data in the sense that a new data point is sampled from the same distribution D. Right? So it comes from this distribution D. And we want to understand what is the chance that this hyperplane that we train on the training data correctly classifies this new data point. Right? So that's what we want to say. Prove that the performance of the learned hyperplane is good on new data. At least if we manage to find a hyperplane with large margins, we want to say that this means that it's also going to perform well on new data. And formally, we're going to measure it by saying we're going to look at the error under the distribution D of this set of parameters W and B, which is just the probability over drawing a fresh sample from this distribution D of getting the label wrong. So what is it? If we're making a prediction, right, we're computing this W inner product X plus B, we're taking the sign of it, and this will be our prediction of its label. And if this multiplied with the true label is less than or equal to 0, we would have made a mistake, right? And if it's greater than 0, we would have correctly classified it. So we're just looking at what is the chance of mispredicting the label, and we want to argue that this is small if you have good margins. And just to make clear, right, that when you make new predictions, we only see X, right? We can make predictions without knowing Y, right? We just need to take the sign of this part. And as I mentioned, right, there's a lot of things already known about this. So let me show you, like, this original work by Bartlett and Shaw-Taylor from '99. So let's spend a little bit of time on this one. So basically saying, okay, so if I get NIID samples, a training data set from an unknown distribution D, where you're promised that all the norms of these vectors are at most 1, then with high probability, so with probability 1 minus delta, over the training data set, right? So the random thing is the training data set here. It says it holds for all hyperplanes that have a margin of at least gamma on all the training points, right? So not just the one output by support vector machines, but it says that any hyperplane that has a large margin to all the training points has a small error under this distribution D. Right, so basically there are two terms here. There's one that depends on the delta, log 1 over delta over n. And there's another one, a log squared n over gamma squared n. Okay. And I guess this 1 minus delta has to be there, right? You could imagine an example. If you're super unlucky, maybe just get copies of the same training point, right? If it's NIID samples, you can somehow be unlucky and get an unfavorable data set. So there has to be some dependency on a delta. There has to be some chance it fails. Yeah.
So is this also somehow saying that if you notice that the margin is big on the sample, then the margin will stay big, like on the float?
Yeah, I guess you could say, yeah, that's almost what it's saying. I guess it's not, so for the proof, it's actually not saying that the margin will stay big. You'll actually see that this gap of gamma is interesting, but it'll say that the margin remains non-zero, or non-negative, sorry, it will remain on the right side. So somehow this margin comes into play in proving this generalization. Yeah, it doesn't stay gamma, but it stays greater than 0 in some sense. That's the idea. Okay. So I guess the bound is saying, right, large margins help, right, because the larger this gamma is, the less data you need to make accurate predictions. So this, I guess, is a theoretical justification why it makes sense to look at the margins. There's also another previous work with a different trade-off. It could also show the same statement, but a log factor improvement in the first term, but a significantly worse dependency on this delta. Why is it worse? I guess it's the same reason as in Josh's talk, that taking square root of a number that is less than 1 makes it bigger. Right? So this is a worse dependency. Yeah, there's also a log in there, right? So these are kind of like, these were the state of the art before our work. You can prove that this dependency on delta is optimal, right? You need a log 1 over delta over n term. It has to be there. I guess that's almost always the case in any of these pack learning things, that there's a dependency that looks like this.
Yeah. And are there results that are more relative to like the covariance of the distribution?
I suppose I have to say I'm not familiar with work in that direction, but presumably there's something. I guess this is also making some assumption at least that this distribution will give you data that is separable. Otherwise, it doesn't say anything. Like, it's an empty statement if there's not a large margin separating hyperplanes. So in that sense, I guess it does say the data distribution is easy if this is possible. Okay. So I guess this is the main result that I'm going to talk about. And I think the reason why it's interesting is maybe not so much for the result, but it's using sketching to prove it, and that's why I thought it would make sense for this workshop. So this is from, I guess it's 3 years old by now. So the result is an improved bound on what generalization error you get if you train a large margin separating hyperplane. Now, maybe you don't remember from the previous slide. So it's a log factor better in the first term. It has the optimal dependency on delta here. And I guess there was also this alternative bound that matched this one in the first term here, but had a much worse dependency on delta. Right? So it's an improvement, or I guess the best of both in some sense. You can also ask, is this the right dependency on the margin gamma? We already know the dependency on delta is optimal. Is it the right dependency on gamma, right? Should it look like log n over gamma squared n? And in this work, we also show a lower bound, proving that, yes, this is the right dependency. You can come up with a data distribution so that with constant probability over this, if I get n training samples, there is a hyperplane that has large margins on all the data, but also has a large error under this data distribution. So it's basically complementing it. As long as your upper bound is saying for all hyperplanes with large margin, you have small error, it's tight. There's nothing more you can do. So it's like the right answer to it. So I guess this is the theorem statement that we'll try to prove, and I'll try to go slow. So I guess this is from here on, it gets a little bit more technical. But this is what we like to prove. We like to prove that if I have, with good probability over training data set, every single large margin hyperplane will have small error under this data distribution D. And the proof is where we're using sketching. So I'll try to maybe do a first kind of motivation for why is sketching interesting, or where does it come into play, and then I'll try to give details that are a little bit more messy. So I guess the starting point is that, okay, let's say instead of having, I guess there are infinitely many hyperplanes that have a large margin. There could be an infinitely many of them, right? So what if there was some set H that contained all the large margin separating hyperplanes, and this set is small, it's some discrete set of hyperplanes. And moreover, it doesn't depend on the concrete training data set. But let's say, just as imagine there's some set of hyperplanes so that no matter what n training points I get, I'm guaranteed that if I had a hyperplane with large margins, it would be in H. So of course, this is not true, right? But let's just pretend that this is true. We'll see how can we use this assumption. Right? So somehow there's a set H that contains all this large margin separating hyperplanes. Then there's a fairly simple way of proving generalization, and that would be, basically you want to show, using just a union bound and standard concentration inequalities, right, that it's very unlikely when I get a new training data set that there is a hyperplane in H that has large margin, while it also has a large chance of making a mistake. Does that make sense? So I want to show this is super unlikely that you can find something in H that has large margins, but also has large chance of mispredicting in the future. Right? Because if I can rule this out, then basically I get the first thing up there. If I can find something with large margins, it will have a small error. Right? Because everything with large margin has small error. So and this proving this is very simple, right? So you can start with, okay, so I have this discrete H. Just look at one of them. Look at one hyperplane in H. And let's assume that this is a hyperplane that actually has a large chance of mispredicting a new point. So let's say, and importantly, right, having a large chance of mispredicting a point doesn't depend on the concrete training data set, right? It's just it only depends on the distribution D, right? So it doesn't depend on what data set do I get for training. So I have, let's say I just have to look at one hyperplane, this one here, and there's a big chance when I get a new data point that it makes a mistake. So basically what I want to argue is that then it's super unlikely that all the margins are large on the training data. Why does that make sense, right? Well, whenever I get a new point, there's a big chance it makes a mistake, right? So that means that the margin is even less than 0, right? When I make a mistake, the margin is negative. And the train data is NIID samples from this distribution D, right? So it would be very unlikely that I don't see a point where I make a mistake. Basically, right, every single time I get a training point, the probability that I don't make a mistake is at most 1 minus the error, or it is exactly 1 minus the error. Makes sense? So this is even the chance of only seeing positive margins, not just margins of gamma, but just seeing positive margins. So the chance I only see positive margins if I often error is very small. And you just approximate this by e to the minus the error times n, and you get something like this. So just by setting, if I have an error that's at least log the size of h over delta divided by n, the chance that this single hyperplane makes no mistakes on any of the training data is at most delta over the size of h, right? And now I can just union bound over all of the hypotheses in all the hyperplanes in this discrete set, right? And say, well, there's only size of h of them, so with probability 1 minus delta over a training data set, there will not even be a single hyperplane in h that both have a large error and all the margins are large, right? Does that make sense? They can just say it's super unlikely that you would see any single hyperplane that has all margins non-negative while also having a large chance of making mistakes. So it's just this completely standard concentration and union bound. Maybe worth noting here, it could be the case that there are no such hyperplanes in H that have all margins large. The theorem statement doesn't say anything like that. It just says it's unlikely that there's something that has large margins while also having large error. It doesn't promise us that there's one that has large margins and small error. But the theorem statement that if I manage to find one on my training data set, I guess that there is one, right? So if I manage to find a good hyperplane that has large margins, then I know that its error is going to be small. So this is basically what you get here.
Where's the number of samples again?
Yes, that's the n, the number of training points. So I guess this goes into the exponent here. Because you have NIID samples every single time, you will see, I guess you'll see a witness to, this one making a mistake. Okay. So I guess in some sense you can say it's highly likely that the training data set is very representative for this this set H of hyperplanes, right? Every single hyperplane in this H, if all the margins are large, it must also have a small chance of mispredicting. Otherwise, you would have seen it here. Okay. So what we'll try to do now to try and generalize this, because we don't just have a discrete set of hyperplanes, right? We have an infinite number of them. The main idea is in some sense to use sketching to map all the large margin hyperplanes to a small discrete set of hyperplanes that's not too large. This kind of makes sense, right? That's what we do in sketching, right? We take some large object or a large collection of them and map them to fewer ones. So that's what we'll try to do. We'll try to use sketching to map large margin hyperplanes to some discrete set H that's not too big, and it will have size exponential in 1 over the margin squared log n. And then if we just plug that in place of H up here, we get the generalization bound we're looking for. Unfortunately, it's not that simple because we can't just sketch it and do the union bound as we did here. We need to be a little bit more careful. But that's the main kind of intuition in the proof, that if we can do this sketch, basically there are not that many different hyperplanes to worry about, only the one for every possible, I guess, bit string or compressed version of a hyperplane. And then all of those will be well represented by the training data set. That's kind of the intuition. So that's like, so what is the sketch in this case? So we're going to allow a randomized sketch. So if I have a hyperplane, we would like to have some kind of sketching mechanism that takes this hyperplane and turns it into a bit string. Right? So I guess the simplest way, you just produce a bit string of k bits. And then we would like it to be the case, if I have a point x, then I should be able to approximate this inner product with w and x plus the bias b. And I want to be able to, just from my sketch of w and b, there should be some function. It doesn't have to be inner products, doesn't have to be, it's just a function, a way of computing an approximation to this, basically to the sign, the margin before multiplying with y. Makes sense? So it's just a sketch that basically preserves these inner products, or allows us to recover the inner products between w and x. That's basically what we're interested in. I guess for proving generalization, it would have been nicer if it was not a randomized sketch, but then it's harder to design a sketch. So I guess there's a trade-off here. And we would like it to be easy to design this sketch, right? So the reason why we allow randomized sketches is to make it easier to give a good sketch. And I guess for the sake of the proof, this decoding function, I guess this f, is allowed to depend on, like, it can see the random choices that are being made by the sketch. If you have some random string that is used to make your sketch, you can look at that during, when you want to estimate this w's inner product with x plus b. Yes, actually, there should not be an absolute value here. That's a mistake on the slides. Forget that absolute value on the slide. You have to approximate it. So of course, it's randomized, and we will allow it to fail. And we will say that for any fixed w, b, and x, I guess here I'm still assuming everything has, both of w and x have unit norm. I'm allowed to fail with probability 1 over n squared. So there's some small failure probability, right, that I do not manage to preserve or approximate w transpose x plus b. And what we're aiming for is k being log n over gamma squared. I think this sketch, I'll get back to what it is. It's basically just JL plus randomized rounding. I think you can almost guess it if you know this kind of work. So the sketching part is not so interesting. It's just JL. But basically the main idea is, in some sense, we'll take all these different hyperplanes and then we'll kind of sketch them into one of these few bit strings. And in some sense, these bit strings will be our discrete set of hypotheses that we're looking at. So the tricky part now, I guess, if we want to come up with, like before, when we assumed there was only a discrete set of hyperplanes we have to look at, what we looked at is really, or we would like that this training data set is a good representation of, for every hyperplane in this set H, the number of misclassified points in the training data set, or the ones with small margins, should be a good approximation of its error under the distribution D. So we'd like to come up with some similar definition here. So let's say we have a sketch, right? So a k-bit sketch, a way of taking, of sketching these W's and B's. And let's start by zooming in. Like before, right, our proof was basically look at one hyperplane and show that it's extremely unlikely that you don't see any mistakes in the training data if it has a large chance of making a mistake. So we're going to do something similar here. So first, we're going to let's start by fixing the sketching, like all the random choices of the sketch, and also the output of the sketch. Right? So look at some output C, so just a bit string, and also fix the randomness of the sketch. Then I'd like to show somehow something similar to before. I would like to argue that in some sense the performance of this sketch C, the one we fixed here on the training data, is very close to its error under this distribution D. So let me try and have a look here. So we're going to do something similar to before. We're going to say, okay, assume that there's a big chance that you see a point. If I'm using this sketch C and I'm approximating this X transpose B, X transpose W plus B, I'm including the label. I'm looking at this. I guess this is an approximation of what the margin is, right? This is what my sketch would approximate that the margin is. Let's say that there's a big chance that I'll approximate the margin to be something less than gamma half. Then I'd like to argue then it should be, then I'll basically see an example in my training data set. I will see one training point where this approximated margin is less than gamma half. This is basically the same as before. Before we said, assume there's a big chance of misclassifying a point, then I'll also see it in the training data. Here I'm just saying, assume there's a big chance of approximating the margin to something small, then I'll also see it in the training data. Does that make sense? Okay, and this is exactly the same proof as before, right? I say, well, if it's very likely that I approximate it to something small, the training points are IID, so I just get n copies of it, and the chance that I don't see it in my training data is super small. You always see an example of a point whose margin is approximated to something small. We're going to do the same as before. We're just going to union bound over all the possible sketches this time, right? Because now I know it's a k-bit sketch, so there's only 2 to the k possible C's. So that's basically how I discretize it, right? There's not too many possible sketches I could have produced. So now I'm going to say, for all the possible sketches, it's very unlikely that if it had a large chance of approximating a margin to something small, I'll also see it in the training data. So basically, this is just a union bound over all of them. So basically, what I have now is I fixed the randomness of the sketch, and then I know with very high probability over the training data set, it holds that every single sketch I could produce, every output bit string I could produce, if it approximates all margins to something large, then there's only a small chance over a new sample that it will approximate its margin to something small. Makes sense? It's basically just saying the training data set will accurately, I guess if you approximate everything to something big on the training data set, it's also very unlikely that a new point will be approximated to something small. So I guess it's just kind of saying that the training data set is somehow representative of all these different sketches at the same time. And I guess there's no promise that there exists even a single C that approximates everything to something large. But if there is, those C will also have a small chance of approximating something to something small afterwards. Okay, so in some sense, we could say that the training data is representative for this fixing of the randomness, right? If I fix the randomness, all the different sketches I could produce are going to behave similarly on the training data as they're going to do on a new fresh point from the distribution. Okay. I have to do one more step. I guess is the difficult part of the proof. So I'd like to somehow come up with a way of saying the training data is nice without talking about the random choice of the sketch. Right, so the problem with this thing is that I have a fixed randomness in my sketch, and then I can say, oh, for this choice of randomness, my training data set behaves nicely. But I like to come up with a statement that doesn't depend on the randomness of the sketch. Somehow just say, this is a nice data set. This is a typical data set. And for this data set, I know all large margin hyperplanes generalize well to new data. So I want to get rid of this fixing of S and F. That's the last step of the technical part here. And for that, I'm just going to use Markov. I guess if the failure probability is only delta over n, I can say something like this. With probability 1 minus delta over a training data set, all the stuff in this blue box holds. With probability 1 minus 1 over n over the choice of the randomness in the sketch, the statement from before holds, right? Every single output in the sketch that approximates everything to something large also has a small error under this distribution. Does this make sense? So this is a property that only depends on the training data set, right? I'd like to get rid of depending on the sketch. So I'm saying my training data is representative if, when I pick my random sketch, if I sketch all the training data to something with large margins, when I try to approximate the margins, it also means that they have a small error under the distribution D, small chance of predicting small margins. So the important part is doesn't depend on the sketch. So let me just wrap up here and see this is enough. It's a technical definition. I'm going to wrap up and then there's be some discussion that's more interesting. So this is just wrapping up the proof. So now we can look at, let's say I have a large margin separating hyperplane, and let's say the training data is representative, both hold at the same time. Then I can look at what is the error of this hyperplane under the distribution D. I guess you write it as the expectation of an indicator for making a mistake, right? Here I'm just saying I misclassified, the margin is less than 0. Then I am going to use the promise of the sketch. The sketch is saying, well, basically, if I have a point whose margin is less than 0, the chance that I estimate its margin to be more than gamma over, or the chance I'm estimating to be less than gamma over 2 is basically almost all the time, right? I know my sketch preserves all these margins. I estimate them accurately. So it's only with probability 1 over n squared that I fail to estimate it to within this additive gamma half. I pull this out as an additive 1 over n squared term. You rearrange the order of expectation and the probability. And last trick is to turn it into something that can use that the sketch is representative. So basically, I split this expectation into those choices of sketches for which there exists a training point that's estimated to have a small margin. And then I guess the other ones where all of the training points are estimated to have a large margin. In the first case, I can always upper bound this term in here with 1, so I just get this term here. And in the other case, I guess I can now condition on all the margins being estimated to something large. So, and then we're done. Okay, so this is the last technical part. The first term here, what is the chance that there exists a point whose margin is estimated to something small? It's just a sketch. The chance that you estimate to something small when all the margins are large is very small. You can union bound over all n points, and all of them will have their margin roughly preserved. And the other part is using that it's representative. So everything that has, so my hyperplane has all margins estimated to something large. It also means there's only a small chance that they estimate to something small under the distribution D. So that's all for the technical proof. I guess I want to show you roughly how it went. So let's wrap up. So basically what I'm saying, if I have this sketch that outputs to k bits, then I can prove generalization that just gets a k in the generalization bound. So that's the main idea. If I have a good sketch, I get generalization here. So it's just saying with high probability over the trained data set, it's going to be representative for this concrete sketch. And so all hyperplanes that have a large margin on the training data will also have a small error under the distribution. And I guess this approach of using sketching has been done before also in these boosting type algorithms, analyzing large margin voting classifiers. I guess that's where the kind of outline comes from. What does a sketch do? I guess I'll just quickly skim over it. The sketch is very simple. B is just a number. You can just write it down in your sketch. It doesn't take many bits to write down a very good approximation of B. You do a sample Johnson-Lindenstrauss matrix into log n over gamma squared dimensions. You project your W into these few dimensions. You randomly round each coordinate to an integer multiple of 1 over root t. Then you get some vector, and then you just write down or whatever this vector is. If you're careful, this only takes O of t bits. You can prove that this works. I'm not going to do it here, but you can prove that this preserves all these approximations to within gamma half with very good probability. So then the final way to make these estimates is just, well, you're allowed to depend on the randomness, so you also do JL on the X that you're about to approximate the margin for. You do the JL, you multiply it with the rounded projected W, and you add this approximated bias. So that's how the sketching goes. And this is basically inspired by, I guess, a JL lower bound by Alon and Klartak as a follow-up of Jelani's and my lower bound for JL. So basically they use this sketch to prove a lower bound for JL. So that's a summary of, I guess, the result. So we get this generalization bound, maybe into the lighter things. I mentioned we had this lower bound that says, with constant probability, there exists a hyperplane with large margins and a large error at the same time, so it's tight, if this is the kind of guarantee you want. In the work, we also generalize it to what happens if it's not all the points that have a large margin, but a t fraction that have a margin less than gamma, you can also prove generalization here. We did that, basically the same approach. I think an interesting question is, well, this is saying kind of like all the possible hyperplanes with large margins generalize well, and the lower bound is saying there exists one that has a large error. What if I run support vector machines? Maybe it's not that one I find, right? I could find something that's better. That could be the case, right? This is just, there exists someone with large margins with a terrible performance. What if I know my algorithm is support vector machines? And very interestingly, this work by Haneke and Kuntorovich that show, so what is this saying is generalization bound says, oh, if I only look at the one that's produced by support vector machines or the perceptron learning algorithm, any of those two, if the output happens to have large margins, then it actually generalizes better than this guarantee up here. Right? So for those concrete algorithms, you can get even better generalization. You can prove, you get rid of this log factor in the first term. So you can maybe analyze, but you have to take the algorithm into account and what it's doing. Interestingly, I talked to Aya just a few days ago, and he said, "Oh, there's a bug in our SVM proof." Right? So the proof, I guess they say that they've been trying to fix it for a while. But the perceptron is fine. So at least for the perceptron learning algorithm, this statement is true. For SVM, I guess technically it's not completely clear whether or not this generalization holds. Then I guess you could ask, okay, can I prove a lower bound for SVM or perceptron? What if it's a concrete algorithm? And then we also, in this work, we also show, well, no matter what your algorithm is, there's a data distribution where the error of whatever your algorithm produces is at least this 1 over gamma squared n. Right? And under this distribution, there's also a good chance that there exists a large margin hyperplane. Right? So basically, I guess this is saying, right, so you can run any learning algorithm, maybe it doesn't maximize the margins. And so so basically, this is saying no matter what your algorithm is doing, it's going to have a large error. But it is possible to find something that has a large margin. Even if your algorithm isn't doing it, it's definitely possible to find a large margin in separating hyperplane. Anything worth saying here? I guess you could say, right, you cannot put it into the algorithm that your algorithm is always producing a large margin in separating hyperplane, because not all algorithms are doing so. So the lower bound has to say something like, any algorithm has a terrible performance, and it is possible to produce something that has a large margin. That's basically what our theorem statement says. Okay. So I guess that's what I wanted to say. The main idea is to try, you can use this sketching technique inside a generalization proof, that you can kind of use it to discretize the number of hypotheses you need to consider without actually using it in your algorithm. Right? That's the main point from this one. Yeah. Thanks.
Perhaps I missed something, but didn't you have the assumption? I'm sorry. Perhaps I missed something, but is the assumption throughout that you are starting with data that is linearly separable?
Yes, yeah, that is the assumption here. In our work, we also have what happens if all but a t fraction of the data has a margin of gamma, then you get some different generalization bound that depends on this. But I think it was already complicated enough, so I didn't want to throw that in as well. But you can also prove something for some data might, outliers and stuff like this. What happens?
I think then the second part of that question is, isn't it almost as much work to figure out if your input data is linearly separable as it is in solving it?
If it's the same,
you have input data, you don't know what it is.
Yeah. Okay, if your input data, okay, so if I want to check whether the input data is separable with a large margin, if that's the only thing I want to check, then you can actually, this perceptron can be made to run very fast. If I check if it has a large margin, I'm not exactly sure whether there's hardness for tiny margins. You can do it in polynomial time at least, but exactly the runtime, I'm not sure.
Any other questions?
So I want to ask a question about what you said toward the end, which you said, like this lower bound just shows that there is a bad separating hyperplane with large margin, but maybe that's not the one SVM finds. But as you defined SVM, the definition you gave, I believe, maybe I misremembered, SVM wasn't an algorithm, it was a problem. It was like, so when you say that, do you mean a particular implementation to solve that optimization problem, or do you mean like the bad hyperplane might not be the max margin hyperplane?
Yeah. Okay. So yeah, for the lower bound, it's saying right, there are hyperplanes that have margins gamma. There might even be some that have a slightly larger or slightly smaller margin. So SVM, if you solve the optimization problem exactly, I guess you'll get some output, and it's for most cases it's going to be unique. So I guess that's what I meant here, and that's what they claimed in this original paper, that the one that I get by solving this SVM optimization problem is going to generalize well. Right, our lower bound statement is, I guess, picking a very particular one that has large margins. Whether it could be the one produced by SVM is not clear. I guess I'm not. One could try to prove that SVM could actually produce the one that has a terrible performance. I don't think that's the case.
To be clear, if that were the case, then it would mean that the bug here is unfixable.
Yes.
Okay.
Yeah, exactly.
Any other questions? Kasper, one more time.